Hello everyone, my name is Mansita Saha, Assistant Professor, Institute of Pharmacy, Assam, Don Bosco University. Welcome to today's lecture on sulfonamides. It is an important class of antibacterial agents, and this is included in the Medicinal Chemistry 3 syllabus. So in this session, we will understand how sulfonamides were discovered, the structure, mechanism of action, SAR, and classification. So let us begin with the historical development first. So before the 1930s, the bacterial infections were a major cause of mortality, and effective antibacterial agents were not available. So one of the main challenges was achieving this thing known as the selective toxicity. So it is nothing but the ability of a drug to target and inhibit only the microorganisms without actually causing any kind of harm to the host cell. So the scientists were searching for agents that could selectively attack bacteria while remaining safe for the humans. So a breakthrough occurred in the year 1932 when the Gerhard Damac discovered that there is a red azo dye, which is known as the prontocell, could successfully treat the streptococcal infection. So this was the first effective systemic antibacterial agent, and it was the beginning of the sulfonamide discovery. Now later in the year 1935, the scientists at the Pasteur Institute discovered that the prontocell was, however, it was inactive initially. It gets inside the body and then it is converted into sulfanilamide. So this sulfanilamide is the actual antibacterial agent which is responsible for the therapeutic effect. Now in this slide, we will see the conversion of the prontocell into the sulfanilamide. So it undergoes the metabolism inside the body and then it gets converted into sulfanilamide and the other byproducts. Now, from this reaction, you can see since it was initially inactive and then it got active, so it is the prontocell basically it is acting as a prodrug. So after the administration only, it is undergoing the metabolic conversion and releasing the active form. So this discovery was extremely important because it led to the development of the several sulfonamide derivatives that were used to treat the bacterial infections. Now let us now understand the basic structure of sulfonamides. So the sulfonamides are derivatives of para-amino benzene sulfonamide. Okay, and as you can see the structure on the right side, it consists of three important portions. First is a benzene ring, a para-amino group, and a sulfonamide group. Now these three structural features are very much essential for their antibacterial activity. Now if you observe the structure carefully, you will see that the structure of sulfonamides closely resembles with the para-amino benzoic acid, commonly known as the PABA. So what is this PABA? The PABA is an essential substance which is required by the bacteria for the synthesis of folic acid. Now, because of this structural similarity, the sulfonamides can compete with the PABA and interfere with the bacterial folic acid synthesis. And this is a part of mechanism of action. We will discuss it in the later slide. So this major thing is that the similarity between these two actually forms the basis of their mechanism of action. Now let's see exactly how this similarity helps in inhibiting the bacterial growth by these sulfonamides. Okay, so before understanding the mechanism of action of sulfonamides, we just compare the structure with the PABA. So the PABA, both PABA and sulfonamides, as we discussed earlier, both contain benzene ring, para-amino group. But one thing is there, that is the sulfonamide group. This sulfonamide groups of the sulfonamides structurally resembles functionally resembles the carboxylic acid portion of the PABA. So because of this similarity, the sulfonamides act as a structural analog of PABA. Okay, so as you can see, this is the folic acid synthesis of the bacterial cell. So what happens? So in bacteria, PABA normally binds to the enzyme dihydropteroid synthase and reacts with the dihydropteroid diphosphate to form all these folate precursors required for the folic acid synthesis. Now, due to the drug's structural resemblance to the PABA, the sulfonamides are mistakenly recognized by the enzyme. So instead of PABA, they choose the drug. Now what happens? The para-amino group of the drug and the aromatic ring occupy positions similar to those of the PABA, while the sulfonamide portion actually forms the hydrogen bonding interactions with the active site. So what happens? The sulfonamides, they bind competitively to the PABA binding site of the dihydropteroid synthase enzyme, and then it prevents from binding. So ultimately, the formation of this dihydropteroic acid is inhibited, and which subsequently reduces the synthesis of the DHF as well as the tetrahydrofolic acid. So if you see the flow chart, you will find that ultimately the main thing happens here is there is loss of or inhibition of the purine and pyrimidine synthesis. Basically, there is prevention of the DNA synthesis. Okay, so all these things happens, and what is the conclusion out of it? It is actually the loss of the bacterial growth or no bacterial growth. Now this is entirely specific for the bacterial cell. Okay, the important part here is to remember that humans obtain folic acid from the diet and do not possess this dihydropteroid synthase enzyme. So sulfonamides actually selectively inhibits this bacterial folic acid synthesis without actually affecting the human cells. So this is basically the selective toxicity that we previously discussed. Okay, now one more thing, it might the question might arise that whether they are bacteriostatic or bactericidal. Now since they just inhibit the bacterial growth rather than directly killing the bacteria, these are considered as bacteriostatic. Okay, uh, any example of any example of antibacterial agents which directly kills the bacteria? It is penicillin. Okay, so it doesn't act like the penicillin, they act like bacteriostatic agents. Basically, they are inhibiting the bacterial growth. All right, so this is the mechanism of action. So overall, you can write down this thing that sulfonamides, it acts as a competitive inhibitor of dihydropteroid synthase, and by mimicking the PABA, um, and thereby blocking folic acid synthesis and inhibiting the bacterial growth. All right, next we'll go for the structure activity relationship or the SAR. So here, as we know, we'll discuss about the first important requirement, that is the presence of the para amino group at the N4 position. Now this amino group must be present at the para position only, because as we know, the sulfonamides acts as structural analogs of PABA. The bacterial cell enzyme dihydropteroid synthase recognizes this structural arrangement only and allows the drug to compete with PABA. If the amino group is suppose removed or shifted from the para position, the resemblance to the PABA is lost. And what happens? The antibacterial activity may be either they decrease or may be completely lost. Okay, so this is very much essential. Another point of this amino group is that it should be free from any substitution. That means that it should not be substituted with anything, because it is important for mimicking the PABA. So hence, for optimum antibacterial activity, you are not supposed to uh, change any kind of or do any kind of modifications in this position. However, there is one modification that we can do, but there is a condition. Okay, we can modify this position, but only if the drug acts as a prodrug. Okay, that means the temporary modification can be done of this amino group, but then the compound should act as a prodrug. So one of the example is phenyl sulfathiazole. Okay, so in when it gets metabolized inside the body, it converts itself into sulfur-thiazole. Now, this is the active form which is responsible for the antibacterial activity. All right. So now let's go to the next point, the benzene ring. Okay, so this benzene ring actually provides the basic structural framework of the sulfonamides. Okay, it maintains the correct spatial arrangement between the amino group and the sulfonamide group, which is very much necessary for the bacterial enzyme to recognize it. Okay, so if we replace it with any suppose aliphatic chains and all, it actually disturbs the arrangement and leads to reduced activity. So yes, the benzene ring should also not be hampered. Okay, next point is the sulfonamide group. Now this is very much essential for activity because the oxygen and the nitrogen atoms are very much important for the hydrogen bonding interactions with the active site of the bacterial enzyme. So these interactions helps the drug bind effectively to the target. Okay, so if there is any removal or major modification of the sulfonamide group, it can result in loss of antibacterial activity. Okay, now coming to the last point, that is the modification in the N1 position. Okay, so we're discussing about this R substitution. So substitution at this N1 position, basically the R, with electron withdrawing heterocyclic groups such as thiazole, pyrimidine ring, all these can enhance the active antibacterial activity. Now why, how? These groups actually increases the acidity of the sulfonamide nitrogen, so it makes the a drug easier to ionize. So this ionized form actually interacts better with the target enzyme. So if it interacts better with the target enzyme, it basically competes better with the PABA. So it has the improved antibacterial potency. So yes, in the R we can substitute, we can modify it by substituting it with electron withdrawing heterocyclic activity. So a lot of points have been covered. So just to summarize, we'll discuss one more time. Okay, there were 5 points. Let us discuss one by one. So the first point, that is the para amino group N4 must be present at the para position. Okay, so its removal or displacement can result in marked reduction or loss of antibacterial activity. Second point, that this amino group should remain free from any kind of substitution for optimum activity. Okay, however, one condition, as we discussed, that it can be substituted if the compound acts as a prodrug. The example you can take is as phenyl sulfathiazole. Okay, the next point is the aromatic benzene ring. Okay, so it provides, as we discussed, it provides the structural framework necessary for proper interaction with the bacterial enzyme. So replacement generally decreases the activity. Next point, the sulfonamide group. This is essential, as we told, that for the interaction we require. So any removal or any kind of major modification can lead to loss of antibacterial activity. The last point, that is the substitution of the at the N1 position with the electron withdrawing heterocyclic groups, as we discussed, like the thiazole, the pyrimidine ring, the oxazole rings. Okay, it increases the acidity of the sulfonamide proton and enhances the antibacterial potency. So examples, you can see sulfathiazole, which has a thiazole ring, the sulfadiazine, which has a pyrimidine ring. So overall, this is all about the structure activity relationship. So we have come to the last segment, that is the classification. So in this classification, I have categorized it on the basis of duration of action and site of action. So first, let's discuss about the systemic infections. First one is the short to intermediate acting. So these drugs actually have a relatively lower plasma protein binding, and they're excreted more rapidly through the kidneys. So they remain in the body for a shorter duration and exhibit this plasma half-lives of approximately 5 to 11 hours. Okay, so these are the examples, some of the examples that sulfadiazine, sulfamethoxazole, the structures are displayed. And next, coming to the long acting ones. So in the long acting, in contrast with the short acting ones, the long acting sulfonamides contain more lipophilic substituents, which increase plasma protein binding and slow renal elimination. So what happens? These drugs remain in the circulation for a longer period of time and produce prolonged duration of action. Examples: sulfamethoxypyridazine, sulfadimethoxine. Next will come for the gastrointestinal infections, the local GIT infections. So these compounds have bulky substituents. Okay, the substituents you will find is bulky, and they reduce the gastrointestinal absorption. So yes, of course, if the gastrointestinal absorption is less, then that means that they are poorly absorbed. If they are poorly absorbed, they remain within that within the intestinal lumen only. Hence, the antibacterial action is seen locally and not systemically. Okay, so the examples I have mentioned here, and the last one is topical use. So they are also formulated in such a way that it directly acts at the site of application, and most of the drugs under this topical use are for used for burns, skin infections, or ophthalmic infections. Okay, so for all these things, so these are some examples that I have displayed. So in all the structures that are displayed here, you can find one common thing that we discussed in the structural activity relationship, that all the modifications are done at the R position, that is at the N1 position. So uh, you will find that in most of the cases, all the modifications we do on the basis of maybe the duration of action, or maybe the area of action, site of action. So on the basis of that, you are substituting it with different groups, but ultimately you are substituting it in the R position only. So yes, that brings us to the end of today's lecture. I hope this session helped you understand the important concepts related to sulfonamides. Thank you for watching.